Hey everyone, so today we are going to look at masked language modeling, specifically in the form of RoBERTa. So this is again going to be a multi-part video series where today we're just going to do a quick primer on RoBERTa, implement a very simple version of it on a very small data set, but after that we are going to work up to attempting to reproduce the RoBERTa paper. So we're going to do a full implementation, train it on lots of GPUs, and see what the results look like. But for now, we just want to take a look and see exactly what is masked language modeling. This is probably new to you if you haven't seen it before, and let's just kind of pick up from there. So let's just first define masked language modeling, and typically this is the way you see it. So let's first set the stage of why we do this before we talk about it. As we've seen, with most transformer-based models especially, the amount of data you need to train these models is ridiculous. And so let's say you want to do a sentiment classification problem. So this is a typical question where you give it a sentence or a couple sentences and you ask the model, is this a happy sentence or a sad sentence? Or is this a good review or a bad review? Or something like that, some type of a classification problem. Well, how much data do you need to do that is basically what I'm asking. Typically, if you're doing an RNN LSTM, you can probably get away with less data. But if you want to train a transformer-based model, especially because you want that long context information and that sort of stuff, the amount of data you need is massive. And so this is a bit of a problem. How much data can you possibly label? Because now someone needs to sit down and label tens of thousands or hundreds of thousands or millions of reviews on Yelp or something like that and label them as good or bad. Sometimes it's easy because lots of online services, people already post reviews and they post a number of stars, and there you go, you have a giant label data set, but it's still typically not enough. So we need a better way. And so there are two typical methods of pre-training that is used today. Number one is masked language modeling or masked modeling. And then the second one is causal modeling. So today we're going to be looking at masked modeling, which will be close to BERT, RoBERTa, some of the other models we're going to be looking at in the future. And so let's first quickly take a look at the two types of transformers before we keep going. We implemented this whole thing in the last video, right? So we implemented the attention is all you need paper, and there was a couple stages to it. You had an encoder. We did an English to French translation problem. And English to French, it basically works this way. You give the model all the English, right? Here's all my English. And then you ask it to generate the French one token at a time. And so what we have here is English first. So to the encoder, this left portion here, we pass in English. And when we pass in English, the model gets all the English, right? This is the sentence I want to translate. So it gets all the English. And so this is known as an encoder because it's bidirectional. The model can look in the future and in the past. So, to learn something about a specific time step, it can look towards future time steps and past time steps to give context to that information. And this is known as the encoder. And it's made of a self-attention, add a norm, a feed forward, add a norm. And that's our encoder transformer block. The decoder is this portion right here, this masked multi-head attention. This is necessary because the French we don't have. We need to generate the French. So there's a causal mask here. Given the history, you predict the next token. So in this case, the model can only look at the past. In the left side on the encoder, it's bidirectional. The model can look both ways. On the right side, the model can only look into the past. So it's unidirectional or causal. We also have this cross attention, but we won't be really seeing cross attention for the next couple of implementations. This will come back again when we do diffusion in the future, so you can kind of put a pin in it for now. So we have an encoder transformer and a decoder transformer. And decoder transformers can automatically be trained on the next token prediction task, the causal tasks that things like GPT, Llama, all those models are trained, and we're going to do a deep dive into Llama later. So don't worry about this for now. I just want us to place our focus here on the encoder transformer, where we can look both ways. So what is masked modeling? Let's kind of take a look. This is a very typical pre-training method for all neural networks. What we do is we take something, data, and we destroy it somehow, perturb it somehow, do something to it, and then ask the model to predict what was gone. One example is in images. You can add lots of noise to an image for lots and lots of steps and then ask it to denoise it. That's your typical diffusion process, right? So you're somehow destroying an image and then you reconstruct the image. And we're going to see all that later. In language modeling, there's a couple ways you can do it, but the most common is this basically delete your words question, right? Or fill in the blank question. What we do is we give the model some text. We'll randomly delete a word or, some words in the text, and we ask the model to predict what was the deleted word. And that's it. Basically it's playing fill in the blank. So if you ever played Mad Libs before, it's just playing Mad Libs, right? You're just filling the blank. You're giving the model some text with some blanks in it, and you're asking what goes in the blank. And why do we do this? So this strategy, this pre-training strategy, notice the input and the output. The input is the data, but destroyed somehow. And the output is the fixed, filled in the blank data. There's no labels here. I don't need labels here. All I need to train this model is a lot of text, which is awesome because text is freely available. I can go to Wikipedia, I can go to a book corpus, I can go to news, I can go to internet, I can go to GitHub. I can download all the text I want and train this model in as much as I want because there's so much available, and I don't need to personally label any of it, at least for the pre-training stage. And what I want you to wrap your head around is this model, when it's randomly initialized, right? It doesn't know anything yet. When it doesn't know anything, we need to train it to understand English, for example. If a model can successfully take a sentence that's missing some words and then fill in the blank, if it can do that correctly, then I would assume that this model understands English. So that hurdle is gone. Basically, the model now understands the language on which it was trained. I can now take this model that already understands English and then just fine tune it to do my sentiment prediction task or my extractive Q&A task, or really any of the other tasks that are available for for what we're trying to do. So again, this is just a quick primer, right, on mass language modeling. But that's the big idea. Take a sentence, remove it, and then predict the missing words on the other end. So what I want to do first is just add some context of BERT. So BERT was the original model that came out, and then RoBERTa came shortly after it, and there were some important differences between BERT and RoBERTa. So first of all, BERT looked kind of like this, and BERT basically had two different things going on in it. First of all, you would provide the model two sentences, right? So you can see sentence 1, sentence 2, so sentence A, sentence B, and both of these sentences were masked. So some of the tokens were randomly selected to be masked. Basically deleted, right? You delete the random words, and there you go, you have some masked sentences. You pass it to the model, and you ask the model to predict what were the missing words. So this is that fill in the blank game, like I already mentioned. But there was also this NSP task, next sentence prediction, where it asked, does the second sentence follow the first sentence? Like, does it make sense? So this would be, let's say you have a data set of like tens of thousands of sentences, and you know which sentences go together. Like if you have a sentence about, talking about the new deep learning algorithm, like it's talking about transformers, and then the sentence after that is talking about golden retrievers. Those two sentences obviously don't go together. But if you have a sentence talking about transformers, and then the next sentence is talking about like, oh, their quadratic complexity or something like that, then those sentences probably go together, right? So that's your next sentence prediction task. This is great, but it leads to some annoyances in implementation and stuff like that. So we won't be doing BERT. We'll be doing basically its cousin, RoBERTa, right? So we can take a look here. RoBERTa, all you really care about are these lines here. RoBERTa adds a couple modifications to BERT. One, they trained it for longer with bigger batches on more data. That seems to always help, right? More data, that sort of stuff. So there you go. They removed the next sentence prediction objective. So it seems like the model actually remains undertrained when you add this NSP task. So instead of having the model do masked language modeling and next sentence prediction, it just does masked language modeling. So they removed this. They also trained on longer sequences. Context length is nice, so that's fine. And then the most important, and what we're going to be spending the bulk of today implementing, is dynamic masking. So in the original BERT paper, what they would do is they actually, they had all their data. They went ahead and pre-masked all the data. So they just, they did it ahead of time, and so the model got it. This means every time the model gets a sentence, like the same sentence, it'll always be the same masks over and over again. In RoBERTa, we will be implementing, or they basically did, dynamic masking. So every time we grab a sentence, we have the full sentence ahead of time, and we will randomly mask it as we're grabbing the batches. And so that's, again, what we're going to spend the bulk of today implementing. And so there we go. We have this. And so, like I mentioned, there's two types, encoders and decoders. Decoders are like your generative models, GPT, llamas, Grok, Phi, whatever, like all your kind of LLMs that you see today, but they're also used in non-LLM tasks like speech or text to speech, right? Generating audio, any kind of generative model really is using something like this. Encoders are our bidirectional models. BERT and RoBERTa are just two examples, but one we're going to be implementing a little bit later is also the vision transformer. It's another type of a encoder. And what you're going to see, and what I really want you to focus on, is as we're implementing these models, we're going to do RoBERTa first, then vision transformers, then we're going to do, I think, wave to vec and a couple other, or masked autoencoders. As we are doing these models one after the other, you're going to see the implementation of the transformer, the implementation of basically everything is very, very similar. Like now that we've actually implemented, so one of the prerequisites actually for this is that you have already seen the attention is all you need sequence. I will try to go into some depth because in case this is your first time watching any of my videos or it's your kind of first time exploring this. But if I'm kind of, glossing over things a little bit, it's because I already spent a ton of time in that video sequence going into depth on attention and all that sort of stuff. So I just don't want to repeat myself too many times. I will link that video down below. You can assume that that attention is all you need sequence is the prerequisite for everything I'm going to do from now on. So that's there. Okay, so we have all this. So we have mass language modeling, computing attention, encoder attention. Again, all this stuff, all these figures actually just came straight from the attention is all you need implementation that I did. So again, please just go check that out because I don't want to say the same thing too many times. Otherwise, all these videos will just end up being ridiculously long. And so what I want to mention or point to now is the masked language modeling logic, okay? So it's not as simple as just, let's just mask tokens. So let's kind of see what this will look like. What we're going to do is, let's say we have a sequence of our tokens. We're going to have a, let's do token 1, token 2, token 3, token 4, token 5, ... Let's say we have 100 tokens. So the masked language model, the masked language modeling rules, or basically guidelines, is this. It's a real tongue twister, but masked language modeling guidelines is select 15%, so 15% as a candidate for masking. Okay? So what we're going to do is we have 100 tokens here. So we're going to select roughly 15 tokens as candidate to mask, right? So we're going to select roughly 15 tokens because that's 15% of our thing. And so let's say we picked, actually I don't have to write it out. So we pick 15 tokens as a candidate to mask. And then what we're going to do is, out of these 15 tokens, 80% of the 15 will be masked, right? So basically replace with the special mask token. So we're gonna have a special mask token. We'll see it in a bit. But basically if we selected, let's say T3 and T5 and some other ones to be masked, we'll delete these, right? Delete these and replace them with a mask token instead of what they originally were. So there we go. That's fine. But we're going to do a couple other things as well. So the thing is that in the real world, when we're fine tuning our model, for example, there are no mask tokens. There's no mask tokens in the real world. We're just doing this masking strategy. So we want our model to see some examples of not having these mask tokens. And the way you can think about it is, if the model knows that, hey, I need to pay attention to the mask token and that's all I care about, then you're going to see that all that effort the model's putting only goes on the mask token. But really you want it to understand the sentence. So we're going to add some extra tasks in there. So first of all, so 80% of the 15 is going to be masked, right? So what we have left is 20%, right? 20% of the 15 is left. So we're going to do 10% of the 15 or 50% of the remaining 20%, right? So 10% of the 15 or 50% of the remaining 20%, because we have 20% left, right? So 10% is 50% of 20%, right? It's half of what we have left. So we will flip or randomly fill with token. So what we're going to do is, let's say we selected more stuff. So we selected this one and this one to be masked, right? So all 4 of these things were selected to be masked, but only 80%, there's probably more, but let's say we're just doing these 4, 80% of them will be actually selected to be masked or replaced with a mask token. And then what's left, for some of them, what we're going to do is fill it with a random token. So this was originally token 2, like whatever token 2 was. I'll just fill it with another token, like, I don't know. I'll just put a question mark here, right? We'll randomly sample a different token and then ask it to, well, that's what it'll get. So instead of token 2, it'll get a random token. And then the other 50% of the time, so we still have the other 10%. So then again, 10% or 50% of, the other half, we're going to leave alone, right? We're going to leave them alone. So for example, in this one right here for T100, we're just going to leave it as T100 and we won't touch it. And that's it. This is our masking strategy. And now what's the goal? What do we want to do? We want the model to predict that this mask token was T3, right? Because that's it. Again, it only got the mask token. It never saw T3. It only got mask token. So we wanted to predict, given the context of everything around you, what is the missing token? Okay, it was token T3. Again, this mask token, we're going to ask it with all the context, T5. But this won't be too bad for the model because it knows that these are specifically mask tokens, right? So, okay, I know this is a mask token, so I know I need to fix it. So to make the problem a little bit more challenging, this 10% here is, hey, this token here is T2. The correct answer is T2, but you got a token that wasn't T2. It wasn't a mask token either. It was just some other token. And you can think about this almost like a spell check, right? The model saw a word in the sentence that was not supposed to be there. And it needs to predict that, hey, this is actually the correct word that goes here. And this is actually a much more challenging task of, hey, this word is incorrect. It doesn't belong here. So T2. And then for T100, this is, again, it'll predict T100. It needs to say, oh, this word does belong here, right? This word actually does belong here. And again, it needs to do all of these predictions with the context of all the other words around it, right? So that's why we're using the transformer, because it gives it that context. And then for everything else, like T1, T4, we don't really care what it outputs here. We won't compute losses on them. We'll only compute the loss on these things that have been selected to be masked, even if they weren't totally masked. So this is the big idea. This is what we're going to be implementing. It's probably easier just to do it than continue explaining. So let's just go ahead and get started with this. Okay, so what we're going to do is, I already did my imports here, so there we go. What we're going to do is be using the RoBERTa tokenizer from Hugging Face. You could obviously train your own tokenizer. We did that in our attention is all you need. I'm not going to bother, right? We're just going to use the existing tokenizer and be happy with it. So there we go. So our tokenizer, is going to be our RoBERTa tokenizer dot from pre-trained. And we're just going to grab the Facebook AI and then the RoBERTa base tokenizer. So there we go. And if we take a look at this tokenizer, it's nice because a lot of these special tokens have already been added in. Some of them being this mask token, which we're going to need, right? That's our mask token. But we also have our start of sentence, end of sentence, unknown token. So a lot of that work is done for us. When we did our tokenizer, right, we had to add these special tokens in, but they're already here for us, so we're good to go. So what we're going to be doing is performing mass language modeling on the very simple Harry Potter dataset that we've seen before. So we're going to start there. And later, in the next couple videos, we'll be prepping a much bigger data set and writing a full reproduction script for this stuff. But today we're going to keep it simple. So we have this. What I'm going to do is create a couple things. So what I want is a list of all these special tokens. So we're going to do special tokens. Special tokens is equal to tokenizer dot special tokens map. Right. So this will give us these are just methods built right into the tokenizer. So this is a list of tokens that I have, special tokens. I am less interested in the special tokens themselves, and I just want to know the index, like what is the number that goes with each of these tokens. So in my embedding matrix, like, what is the index for each of these things? So we can do that. We can create a special tokens dict, create an empty dictionary, and we can do for token in special tokens dot values, right? So we want to iterate through the values of this dictionary. So that's the same. We're going to loop through all of these, and we're just going to do special token index. We're going to store for this token the number that represents it. We can just encode them, right? Tokenizer dot encode, and we can do token. But when let's fix that. Special token index. Special token index. Let's see here. Right, dict, not index. So let's fix that. There we go. All right. And so what you can see here is, yeah, we do have our special token. So we can see the mass token, for example, is 50,264. The pad token is 1, unc is 3. But we also get these extra 02s around it, which we don't need. So we can just index it for 1, right? So that'll grab the one that we want. And there you go. Those are our tokens, right? The number that represents each of these tokens. So if you have any confusions on tokenizers, again, just go look at one of my previous videos or look online. They're pretty straightforward. It just converts numbers to words to numbers, right? So there we go. And what I want to do, you're going to see why we need this later, but basically at this stage, right, we need to randomly sample, right? When we do this 10% right here, we need to randomly sample a token to kind of replace an existing token with it. So we're going to look in our tokenizer and just just randomly replace it with something else. But when we replace it with something else, we only want to replace it with an actual token. There's no point of replacing it with a special token. So we just need to ensure that we just have a list of our, these are our token special token indices, 0, 2, 3, 1, and 5264. And then we'll have another token index, or basically a list of tokens of all of our regular tokens. So let's just do that. So all tokens index is just list range, what do you call it? Tokenizer dot vocab size, right? So this is basically, we have, let's see, if we print out our tokenizer dot vocab size, you'll see we have 50,265 tokens in this tokenizer. That means our indexes for the tokens go from 0 to 265, to 50264, right? 50,264. So what I want is my all special tokens, right? Special tokens. These are just the ones that we already saw, right? So we're going to do list special tokens index dot values, right? Values. So all special tokens. So these indexes, dict. Fix that. These indexes are specifically special tokens, right? So these are the indexes of our special token. And so the indexes of our non-special token is everything that's in our list of all possible tokens minus these here. And so there's a couple ways we can do that. Easiest ways, we can do our all non-special tokens. So all of our regular tokens for all our text is just going to be token for token in all tokens index if token not in all special tokens. So we just want to grab every single token in this list that's not in this list. And there we go. We now have all of our special tokens, a list of special tokens, and a list of our non-special tokens, which we're going to use later for sampling random tokens from. So there we go. This next part I'm just going to copy in because it's not interesting. It's just a little bit of a data prep, but basically I'm looping through my Harry Potter files. If you saw my LSTM stuff earlier, then you'll probably have seen something like this already, but we're just prepping the Harry Potter dataset a little bit. And all I'm doing is I'm loading in all the text files for a Harry Potter dataset. We can actually look at what that looks like, text files, right? We have a couple of text files, one for every single book of Harry Potter. And all we're going to do is loop through them, load the book, and then just clean some stuff up. So there's like page numbers that we don't need. There's like new line characters that we can remove, and just a little bit of cleanup, nothing fancy. So that's all. I'm just going to leave that right there. And there we go. Now we have all of our text. And if we just look at our all text and just look at the first like 1,000, right? There we go. That is our text for this specific, all of our books. And so if that's our text, what we need to do is chunk it up. So we obviously can't pass the entire text and everything, so we just need to chunk it up. I just decided that doing chunks of like 5 sentences at a time is reasonable, so we're just going to do that. I'm going to do all text chunked. Actually, no. We're going to do all text. Let's see. Text is going to be our all text dot split. I'm going to split on the periods. Now, I'm assuming that a period is a sentence, like end of a sentence, but obviously that's not true because we have like Mr. and Mrs., but it's fine. We're going to basically chunk these up into sentences to the best of our ability. This is just an approximation. There's better ways of doing this, and we're going to see better ways of doing this later. This is just to get the point across. So all text chunked. This is just going to be, we're just going to loop through our text. So all text from I to I plus 5, right? So we're going to grab chunks of 5 for I in range from 0 to len all text, right? We're going to go in from 0 to the end, but we're going to go in step sizes of 5. So this will basically grab the first 5 sentences and then the next 5 sentences and the next 5 sentences and so on and so forth. But this will just, these are lists, right? So each of these things will be a list. We just want to put those lists back together as sentences. So we're going to put the period back. So we can do period dot join all text, right? So this is just a dumb way of cutting our text up into somewhat 5 sentences. And let's just take a look at the first 5 things. So this is our first chunk. This is our second chunk. This is our third chunk, so on and so forth. So these are our chunks of text that we've done. And you can play with the chunk size, but this is fine for now, right? We're not doing anything crazy, and so we should be fine. All right, now that we have chunked our text up, it's actually time to do the important part. We need to tokenize all this text. Like this is fine, but we don't need words. We want numbers that represent them. So we're going to do tokenized text. Tokenized text is going to be equal to, we're just going to do list comprehension again, tokenizer.encode text for text in all text chunked, right? We're going to just loop through and we're going to tokenize all of it. And we can look at the first 5 again, tokenized text, and let's just look at the first 5. We'll give that a second. This will throw a warning, I think, on one of them. There we go. One of the sentences is longer than 512 tokens, which is the maximum length that the original RoBERTa implementation that Hugging Face has can accept. So it's just throwing a little warning here saying, hey, I have more than what the model can handle, but that's fine for now. We don't really care. So you see here we have our tokenized text for the first sentence, tokenized text for the second sentence, so on and so forth. But we still have a little bit of a problem, right? We haven't padded anything. We haven't put them together. Each chunk is of a different length. So we have a few things we need to do. And so let's go ahead and start that. We're going to write our dataset class now. And we're basically going to do what I described. We're going to first pass in a token or a sequence of tokens. So here we go, like any one of these sequences. We're going to pass in this sequence of tokens. And we're going to select 15% of them for a candidate for masking. We're going to pick 80% of that 15%, actually replace them with that special mask token. I already got rid of it, but that special mask token that's inside of our tokenizer, right? So we're going to do that. And then once we have all of that, then we can basically, wrap this up. So because you'll see the model implementation is actually basically identical to what we've done before. So this is where the bulk of our efforts are about to go. So let's go ahead and get started, and then we'll add in more details as we keep going. So I'm going to create a class called MastLMLoader. One thing to keep in mind though is the implementation we're doing today is sample by sample. So we're going to be masking each sample individually, which is fine, but it's obviously best to do things in batches. So when we do our full-blown example in the future, we'll actually be basically re-implementing the same logic, but to apply on batches of data rather than just a single sample at a time. But other than that, it'll be basically the same. So we're going to set some maximum length. I'm going to set this as, I guess it's fine for now. Let's just leave it. And then masking ratio is 0.15, right? Because we want to mask 15% of the stuff as candidates for masking. We're going to do self.data is tokenized data. Self.mask ratio is our masking ratio, and then self.max sequence len is the max sequence len. There we go. And we can set here, so let's just create it. We can do MLM is our mast LM loader, and we're just going to pass in our tokenized data, which we called, let's see, what did I call it? Let's make you smaller. I called it tokenized text. So there we go. Tokenized text. And so we can do for sample. Actually, we can't do that yet, but yeah, let's look at for sample in MLM. Let's just break. And so every data loader, just like always, will have a len def len self, and we just return len self.data, right? So how many chunks do we have? That's, however many chunks we have in self.data. And then we have def get item, right? Just like always, self index. And we're going to do our data is going to be equal to self.data index, right? We're just going to index out the data, and we're going to make sure this is a tensor, torch.tensor. Now, if the number of tokens, so let's actually make this 25 for now, just to make sure it's shorter. If the number of tokens here, right, in our data, in this specific sample, if this is longer than the maximum length we want, then we have to do something. And there's a couple things we can do. We can either say, oh, if it's longer, just take the first 25 tokens or take the last 25 tokens. Or we can just grab a random slice of 25. So for example, if we have 100 tokens and we only want 25 of them, we can grab any 25 consecutive tokens from here. So easiest way is just sample a random starting point and go from there. So we can do our if len data is greater than max sequence len, or so if you have more tokens than we want, then we can do a rand start index, right? Just randomly pick something, and we pick between random dot choice, choice is with the C, list range len data. Now the problem here is, let's say we had 100 samples, right? So len of data is 100 in this case for this specific sequence, and we wanted 25. And we random sampled 90. That means our index would start at 90 and go to 90 plus 25, right? Which is over 100. So that's a bit of a problem. So we're just going to offset this, right? The len of data is fine. We're going to subtract from it self.max sequence len. And there we go. So this will ensure, and I need to make sure this is a self as well. There we go. So this will make sure that we'll pick a random starting point, but this basically the highest starting point we can, because we want to make sure we don't go over, because you don't want to, try to index tokens that aren't there. So in this case, if we want 25 and we have 100, the maximum I can pick is 75. So I can then index from 75 to 100 and get my 25 tokens. So that's it. So then our end index is going to be just our random rand start index plus self.max sequence len. And so our data is then just data and index from rand start index to end index. And that's it. Right, so we're just going to grab a random slice, nothing crazy. And now here's for the hard part. We need to basically perform this masking strategy that I already mentioned. So we're going to do self.random random mask text. And all we're going to pass to here is our data. So we have to write this method now, def random mask text self, and we pass in our, I call it token. So we're going to do that. We can print the tokens right here. And these are the tokens we need to do. And let's put this back to 100. So there we go. So these are the tokens we need to mask, right? Do the masking strategy. So let's kind of remind ourselves again, right? Here's our tokens. For now, we don't actually have pad tokens. When we do it later, in the batching, then we will, but for now we don't have any pad tokens, so ignore these for now. So all we have is just tokens, a sequence of tokens, and we're going to randomly select some tokens for masking. So you can see that I picked here randomly that 5 was selected to be masked, and 4 was selected to be masked. So that means at these specific mask tokens, the correct answer was 5 and 4. But notice here the 6 was randomly changed to a 26, but the model still needs to predict that this is a 6. So that's the key idea, right? We have a 5, we have a 6, and a 4. The 5 and 4 came from the masking. The 6 is the model needs to know that this word does not belong. 26 does not belong here. It should be 6. Again, enforcing the idea that the model needs to understand the full sentence and what words mean rather than just this masking strategy. Okay, good. And the last part is, what are these negative 100s? And when we compute our loss, we only care about what the model predicts for things that were candidates to be masking. Anything that's negative 100 will be automatically ignored by cross entropy. So if you look here in torch.nn.cross entropy loss, the ignore index is negative 100. This means any label that's negative 100, as you see here, any label that's negative 100 will be automatically ignored by cross entropy loss. So it just won't be in the loss. So the only things we'll compute losses on are things that were candidates to be masked. So that's things that were masked tokens, things that were randomly perturbed, or things that were left alone, though I don't have an example of that here. So let's go ahead and now implement the full 80-10-10 masking strategy. So we have tokens. There's a bunch of ways you can actually do this, but the easiest way I think is just by just kind of creating subsets. So let's do this. So we can do random masking. It's going to be torch.rand, and we're going to pass in our tokens.shape. We're going to unpack that. And what you'll see here is random masking. And let's also just print out the tokens as we go. Print tokens. So what you see here is these are our tokens. And what I've done is generated a noise vector. So first of all, rand is standard uniform. So that means we're generating numbers between 0 and 1 uniformly. And what we're going to do is any number here that's less than 15% is going to be a candidate for masking. So that means 0.12 is candidate for masking. This is not, I don't know. I'm sure there's other ones in here, but here we go. 0.09 is a candidate for masking. 0.06 is a candidate for masking. Anything that's less than 15% is going to be a candidate for masking because we want 15% of our data to be masked, right? Or a candidate to be masked. And so yes, so anything that's less than 15% is going to be that. Or you could run anything greater than 85%, right? It doesn't matter which direction you do it from, it's up to you. So we have our random masking here, but there's one thing to keep in mind. Remember the 0 and this 2? These are special tokens, right? Like a start of sentence and end of sentence token. We do not want to apply any kind of masking on special tokens, like whether it was bad tokens or if it was unknown tokens or the special tokens like start of sentence, end of sentence. It just doesn't make any sense to apply our masking strategy to that. These are just filler things that we add in. We want to apply masking strategy to the actual text itself. So everything in between in this case. But notice here, the first token 0 just got a probability of 0.0069. This is less than 15%. That means this 0 here, a special token, has been selected to be a candidate for masking. This is not good, right? We don't want this. We don't want to do this. So what we're going to do is for all special tokens, we're manually going to set those values to 1. And 1 is greater than 0.15, so we don't have to worry about them, right? So anything that's a special token, we're going to set them to 1, just so we're never ever masking special tokens in any way. So we're going to go ahead and do that first. So that's our first kind of exception that we need to handle. So special tokens is going to be basically a tokenizer.get special tokens mask This is a method that's basically built right into the tokenizer. We could obviously also just like do it ourselves because we have the list of special tokens, but it's fine. We're trying to use the tools that are available to us without having to write too much more stuff. So we basically want the special tokens inside this token. So this will basically return a 0, 1 vector, or maybe a true false, I can't remember. I think it's 0, 1 vector that tells me for 1 is a special token and 0, it's not a special token. And we just have to give it this flag that it already has special token as true. So it doesn't need to add any special tokens. It will just look for the ones that are already in there, and we can do special tokens. It's just a 0, 1 list. Right, so we can see that the first token is special, or start of sentence, and the last token is special, end of sentence. And everything in between is not special. Right, so there we go. As a list, it's kind of useless, so we're going to convert it to a tensor. So there we go, torch.tensor. So start of sentence, end of sentence. And all we're going to do is in our random masking, we're just going to set everything special tokens equal 1. Any place where special tokens is 1, because again, the shape of special tokens and random masking are the same. They're both vectors of the same length. So any place where this is 1, I'm going to set my random masking to 1. And so now if we print out random masking, you'll see that the beginning of sentence is 1, the end of sentence is 1. And so because these are both greater than 0.15, they will never, ever become a special token, right? Or become masked, or become a candidate for masking. So we're good to go there. That's our first kind of exception we need to handle. Now we need to create our labels. By default, everything is -100. So by default, we're going to set everything to -100, but on things that were selected to be masked or candidates for masking, those are the labels. So regardless of if we fill it with the mask or if we perturb it, we just need to have a vector of these labels. So we're going to create a vector of -100s, and at the indexes where things are being masked, we're just going to fill them in with the correct answers. So it's basically our original data, just -100 everywhere it wasn't masked. So we can go ahead and do that. We can do our, let's see, first up, random masking. It's just going to be random masking less than self dot mask ratio. So this will give me a random masking. It'll give me a true false of which tokens were selected to be masked and which tokens are not selected to be masked, right? So there we go, or candidates to be masked. So there we go. Now that we have our random masking, we can use this as a flag. We can do our labels is going to be torch.full. And so torch.full is just an easy way to do this. So tokens.shape. We want to create a vector in the same shape as tokens.shape. And we're just going to fill it with -100. So if we print out our labels, we've just created a vector, basically our labels, all with -100s. And this is again in the exact same shape as our tokens and our random masking and everything else. But what we want to do is just populate this with the correct answers on the tokens that were selected to be masked. And so what we can do is labels, and where random masking is true, right? So on the indexes where they're true, because random masking is currently a true false Boolean, we're just going to fill it with our original tokens, again, where it's true. Right, so this is just a shorthand. We can print out our labels. It'll look kind of like this. So we have -100 everywhere, but the tokens that were selected to be masked or candidates for masking, we now have their labels. And only on these values are the losses actually going to be computed in the end. I'm going to run it again. And there you go, right? So we have our candidates for masking there. But just because we have a 9 or a 7 or 28 here doesn't mean we have a corresponding mask token. So now we need to do the 80-20-20 split. And there's a couple ways you can do this, but this is probably the way I like doing it and is the easiest way of doing it. What we have is print random masking. What we have is just a true false list, right? This is saying the first token is not masked, the second token is not masked, the third token is not masked, fourth, fifth, sixth, but the seventh and eighth token are masked, right? These have been selected to be candidates for masking. And so what I really want is the index, right? Like which indexes were selected to be masked, like the 8th word, the 9th word, the, so on and so forth. So what indexes were selected? This is different from the tokens themselves. This isn't like this is literally which word in the sentence, or the index of the word was selected to be masked. Not the word itself, but the index. So this would be like 8 and 9. So word 8, word 9, 10, 11, 12, 13, 14, whatever, dot, 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 which words are selected. And so the easiest way to do this is dot non-zero. There's a nice little method built right in, and there you go. So these were the indexes, the positions of the tokens that were selected to be masked. The 7th token, the 17th token, the 32nd token, dot, dot, dot. These are the things selected to be masked. And what I want to do is 80. So this is my 15%. This is my 15% of my data selected to be candidates for masking. 80% of these tokens will actually be masked, right? So we're going to select 80% of these at random to actually mask them. And then of the remaining 20%, 50% of that 20%, so 10%, will be randomly changed to a different token. And then the remaining 50%, the last 10%, we're going to leave alone. We won't do anything with them. And for all of these things, we have its corresponding correct label already stored in labels, right? So it's already in here, ready to go. And so now it's just really the decision of, I know what the correct answer is for all of these positions, but what do I want to put in these positions? Do I want to mask them? Do I want to randomly perturb them? Or do I want to just leave them alone? And that's basically what we need to build now. And so to do this, step 1 is basically what we already did. We are going to create another masking flag. So I'm going to call this random selected index, right? So these are my randomly selected indexes for masking, candidates for masking. I'm going to create another masking flag. But this time it's going to be torch.rand, so it's still uniform, but it's going to be on our random selected index. So it's going to be on this tensor. So we're just generating a random number between 0 and 1 for each of these numbers. And if we take a look, it'll look like this. Print masking flag. Looks like we have a issue here. Try to allocate memory, right? So we need to do dot shape, right? We need to unpack. There we go. So this is my randomly my randomly generated things. And now 80% is what we want to keep for masking. So that means anything less than 0.8 or greater than 0.2, up to you. Anything less than 0.8 will be selected to actually replace with the mask token. So that means if we print out our, again, random selected index. So let's take a look here. This is less than 0.8. So 0.68 is less than 0.8. So that means the token at position 26 will be replaced with a mask token. 0.39 is less than 0.8. That means the token at position 28 will be replaced with the mask token, ... So these are my positions, right? This token here, 0.84, is greater than 0.8. So that means this 5 here, the token at position 5, can either be half the time it'll be replaced with a random token. That's the 50% of the remaining 20%, giving you the 10%, or just be left alone. And we haven't gotten there yet. So first up, we just need to do the 80% rule. So let's go ahead and do that. So we're going to delete you. Let's get rid of you as well. There we go. Okay, so first up, we have our masking flag. So just like before, masking flag is going to be our masking flag less than 0.8, right? Just like what we talked about. And so now if we print masking flag, it's just going to be a true false boolean, right? These were selected to be replaced with mask tokens. These will be left alone and we'll deal with them later. So now that we have that, all we need is our selected index for masking is going to be our random selected index. And we're just going to filter it with our masking flag, right? So all I want is, these are all the things that were selected to be masked, or candidates for masking. I'm just going to filter them for the only ones that were true. So here we go. Print selected index for masking. There we go. So these indexes, so these positions, so the token at position 6, the token at position 15, ... These indexes of the positions were selected to be replaced with actual mask tokens. And we'll see that in a bit. On the other hand, we have the other half, right? We have our unselected selected index. Again, for masking. So this is everything that's left over. And that's just going to be the same random selected index, but we'll flip our masking flag, right? So we want everything that wasn't selected to be masked. And if we print that out, print unselected index for masking. So we can see these were tokens that were not selected to be masked and will fall into the next rule. 50% of this will be randomly swapped to a different token, and 50% will be kept and left alone. So let's do that part now. So again, how do we do the 50%? 50%, just like how we did before. We're going to create a new masking flag, right? Masking flag, again, torch.rand. But this time, we're going to do the masking flag on the whatever's remaining, this unselected index for masking. Dot shape. And there we go, right? In this case, again, it's random, right? So every time I run it, in this case, I have one token. In this case, I have 4 things. I could also have no things, right? There could be nothing in here as well, and we'll have an exception for that a little bit later. But for now, this is good to go, right? So we have our masking flag, and that's it. So we have everything we need. And so just like before, we're going to do our masking flag is going to be masking flag less than 0.5. We're again doing 0.5 because we're doing 50% of the remaining unselected, which is 10% of the original, right? So we selected 80%, leaving 20%. Of the 20%, 10%, so of the remaining 20%, 10% is going to be randomly changed. Well, 10% out of the 20 is 50% of the remaining. So there we go. We're doing 50% here. So there we go. Masking flag. And then we're going to do selected index for masking. Or actually not masking. This is going to be selected index for random filling, right? These are going to be the ones that will just randomly alter to some other random token that the model needs to know doesn't belong here. So we're going to do unselected index for masking. All right, we're going to basically go in here and again, just filter it for things that were selected as true, right? So things that filled our criteria of less than 50%, grab those corresponding indexes. And then we have selected index to be left alone. These are the indexes we're not going to do anything with. Again, it's just going to be exactly the same thing. We're just going to flip our masking flag. And so we end up with this print selected index for masking, print selected index for random filling, and then we have print selected index to be left alone. And there we go. So here's an example where something was not selected, or so we have an empty tensor here, right? So that can happen. Like in this case, we have a pretty short sequence. There's just 100 tokens. So it's totally possible that something was not selected because it's random, right? So we might have just ran out of tokens. If we run it again, maybe we'll get a different result. In this case, we see the other one. These are ones that have been selected to be changed. Again, there's nothing in there. That's just the typical randomness. Here's one where all 3 of them are met. So these are all the tokens that we're going to, or the positions of the tokens that we're going to replace with a mask token, right? So all of these will be replaced with our special mask token. This index at index 52, so the 52nd token in our sentence, we're going to replace it with some other random token, whatever it may be. And then the 56th token, we're going to leave it alone. We won't do anything to it. And so this is basically your masking strategy. Every time you run it, right? Again, it's not perfect. If you had more text, if it was longer, then it's less likely for this to happen. But you could always just run out of tokens to sample, right? So there we go. Now that we have this, let's go ahead and actually do the filling, the randomness, all that stuff. So we're going to do if len, this is our condition, selected index for masking greater than 0. Right, so there we go, greater than 0. What we're going to do is if something was selected to be masked, then we're going to fill those tokens with its corresponding mask. So let's actually take a look at this. Let's say we have torch.tensor and we have 1, 2, 3, 4, actually let's do different numbers. 10, 2, 5, 1, 7, 2, whatever. right? So that's my tensor. Let's call it A. And what I want is the second, so the first index, so 0, 1. I want the 2, I want this one, and I want the 7. So we can actually index it kind of with using a tensor. We can actually do torch.tensor. And we can say I want the first index, I want the fourth index, and I want the fifth index. And we need to make this a list. There we go. So we're indexing a tensor with another tensor. And there's other ways you can do this. You can use torch.gather or scatter. Like there's other methods for this, but I typically just like doing it this way because it's easy for me to understand. But basically I'm saying I want in A the first value, the fourth value, and the fifth value. So that's the 0, 1, 2, 3, 4, 7, and then 5 is 2. So there you go, 2, 7, 2. So I'm indexing a list, indexing a tensor, a vector, with another vector, effectively. We can actually do this for multi-dimensional stuff too. We can, but for now, well, we can do it instead. Actually, for now, let's leave it. We'll need to do multi-dimensional ones when we do a batched implementation of this. But for now, we're trying to keep it simple. So we're going to leave it as is. So if we have a selected index for masking, what we're going to do is do our tokens, and we're going to index it. Remember, these are indexes. Like this is saying this specific position of token, this specific position of token. So there's indexes. So I can just index like this, right? I want my tokens at these positions, and I want them all to equal to my mask token, my special mask token. So I can look at special token dict and just pop in my special mask token. I bet I spelled something wrong. Let's take a look and see what I called it. Special tokens dict. There we go. All right. So that'll be right here. Okay. And we can now go ahead and print tokens. And you'll see I have populated with my special token, right? 50264 was my mask token. I've populated this sentence with my special tokens at the ones that were selected to be converted to mask tokens. So we can actually print that out. Print our selected index for masking. So selected for index for masking says the sixth token should be masked. Okay, so 0, 1, 2, 3, 4, 5, 6. Okay, that's a mask token. The ninth token should be masked. So 6, 7, 8, 9. Okay, there you go. The ninth token is masked. So these are just indexes. And all I did is reach into my tokens, grabbed for these specific indexes. I just want to convert them all to our mask tokens instead of what they originally were. Right? If we print the labels real quick, you'll see that in this case, let's run it again so maybe there'll be something at the beginning. Here we go, that's better. So our data is 0, 7, 0, and then 73, the 73rd token. And then we have our mask token. And the mask token should be 1941. So that's the corresponding thing we need to predict. This mask token should predict 9963. This is fine. This is fine. This is an example of, hey, I have a sentence and I left this token alone. So notice it's not a mask token. So I left it alone and I need to predict that it is itself. So this is the correct token to go here. Here's another example. This is a token that needs to go here. Here's another example. Is there another one of the other types of examples? Let's see here. So 27, nope. Okay, it's fine. Well, we'll see. Maybe we'll see one a little bit later. 215. Nope. So that's another mask token. We need to predict that. Okay, it's fine. So it's fine. So we actually haven't completed everything yet. So let's just keep going first, and then we'll come back. The problem, as you see, is yeah, this is fine. So we're doing it correctly. We need to do the other half. So these are the ones that have been selected for masking, and we've populated them. Now what we're going to do is the random filling. So we're going to do if len selected index for random filling greater than 0. So if we have tokens in here that we've selected to just replace with another random token, well, first off, we need to sample some tokens. So let's see here. So these were the indexes selected to be tokens, but we can see there's 2 of them. So what I need to do is just randomly sample 2 tokens and then replace these 2 tokens at these 2 positions with my randomly sampled tokens. So what we're going to do is our randomly selected tokens is just going to be random.choice, right? Just random.choice, or actually random.sample. And we're going to sample from our all non-special tokens index, right? Because again, we only want to sample from things that are not special tokens. It wouldn't make sense to replace this token with a mass token or a pad token or something else. So only from our non-special tokens will we sample it, which is why we just made this separation out up here, right? We just made a list of non-special tokens so we can sample from them now. So there we go. We're going to sample from here. How many do we want to sample? Well, however many spots I have. In this case, 2 were selected to be replaced with a random token. So we need 2 of them here. So, or in our case, it's going to be len selected index for random filling, right? So however many tokens are inside this thing is what we're going to do. And then we just need to convert this to a tensor. So torch.tensor. And this is basically me randomly selecting 2 tokens from my list of all possible non-special tokens. And all I need to do now is populate my tokens at those selected indexes for random filling and just fill them with our randomly selected tokens, right? We're just going to populate them. So at the indexes that we decided we want to randomly change something, well, fill them with the things we randomly sampled and we're good to go. And that's it. We're going to now return our tokens and our labels. There, for the last part, it's selected index to be left alone. There's like, we want to leave them alone. There's nothing to do there. And so this effectively concludes our full masking strategy when we're doing a single sample at a time. When we do it for batches, it's going to look almost identical to this. We just have to add in some extra logic to just, do it in batches rather than a single sample at a time. So there we go. And so we can look at our over here. So this will return our tokens and labels. And we can print out our tokens and print out our labels. And let's just see what it looks like. And actually, instead of looking at all these -100s, this will be easier to look at for things that aren't -100. So let's just filter it. So you want to look at this for where labels not equal to -100. We're just going to filter it out to make our the visual a little bit simpler. There we go. What are we missing? All non-special tokens index. Let's see. What did I call it? All non-special. Oh, it's just all non-special tokens. There we go. There we go. All right. So we can see here, this is a mass token, right? So I filtered out. I filtered out for things that were, things that were not candidates to mask. This is a mass token. This is what I predict for it. This is a mass token. This is what I predict. This is a mass. This is what I predict. And we just repeat this over and over again. Let's see if we can pull out one of those other types of examples. Mask token, mask token, mask token, mask token, 182, 182, 17, 17. Looks like we didn't get an example here. Okay, here we go. Here's one. So for these cases, we have these mask tokens and we want to predict their corresponding token. Here, I filled it with a random token. So this is a random token that I picked, and this is the correct answer. So the model needs to know that, hey, this word does not belong here. This is the token that belongs here. And again, this token does not belong here. This is the token that belongs here. So it's a little bit more challenging than just filling in the blank, right? It also needs to understand that some words belong and some words don't belong. And it doesn't get the primer that it's looking for mass tokens where this happens. This can happen anywhere, and it doesn't know where to look. Good. So now that we have all of this, we can return our tokens and labels. And we have now effectively completed our data set, right, with random masking. Now, random masking on its own is fine, but we still need to do our data loader because we don't train on a single sample at a time. We train on batches at a time. Today, we're going to write a very kind of dumb data loader, but it should work just fine. For this case, we'll write a smarter one later because we'll effectively be putting all of this stuff and all of this stuff together basically in the future, but for now, it's fine. I'll actually do it down here. So we're going to do def collate function. So if you don't remember, the collate function is where we stick our samples together. So this is where we can define our padding logic or our whatever else we want to do. So that's all going to go in the collate function, and we provide the collate function a batch. And so what this looks like is let's go ahead and print the batch. And we can define a data loader, right? So we can do loader is our data loader, and we want to do it on the MLM dataset. And let's just do a batch size of 2 for now to make it visible. And we need to provide it the collate function. So that's going to be collate function is the collate function. And we can do for sample in loader, and we can break. So you can see the batch is basically 2 tuples, right? Because every sample is going to return tokens and labels. So here's the first one, tokens and their corresponding labels, and then tokens and their corresponding labels, right? So we just have, batches effectively. And so first, we need to kind of split them up. So let's do this. We're going to do our token samples is an empty list, and our label samples is an empty list. And we're going to do for token label in batch. We can do token samples dot append token, and then label samples dot append label. So all I've done is just take my batch and split it into 2 separate lists of tokens and labels. And what I want to know is what is the maximum length in this sequence, right? In these tokens, what's the maximum length? So we can do max len, which is the longest thing, because we need to pad to the longest thing, right? So we're going to just add these pad tokens until we reach all the batches, reach whatever the longest sample in the batch was in this case. So that's just going to be the max of our len token for token in token samples, right? So that's all. So all we've done is we're going to loop through our token samples, right? Each one of them. We're going to take the length, find the length of how many tokens are each one of them, and then just find the max of that list. And this should give us our max len. And you can see it's 100. So one of our sequences is 100 long because that's what we set as the maximum in this case. So there we go. That is our tokens. Now that we have that, we can go ahead and do this. We're going to create a padding mask. So padding masks is an empty list, and we're going to populate this and it'll make sense. Again, all of this will be batched and done much better in the future, but for now, just bear with me. For index in range len token samples, right? So token samples. So what I want to do is loop through the number of samples I have in this batch, right? So that's however many things are in here. And we can do our sample. We can just grab it. We can get that from token samples, and that's just at that specific index. And then our sequence len, right, is just going to be our len of this specific sample. And we also can grab the label, right? So label is equal to label samples at that specific index, right? They go together. We have our sequence len. And I think that's all we need. Oh, right, one more. We can do diff. So diff is going to be our measure of how much shorter is this sample from the longest sample. So max sequence len, or max len, is the longest sample in this batch. And what I want to see is compare my current sample that I'm looping through to the longest sample in my batch. And so it's going to be max len minus our sequence len. So there you go. That'll tell me how much it is. And if you look at our diff, print diff. Looks like we have a bug. Label samples, spelled something wrong. There we go. We can see the first sample is 26 shorter than the longest thing, and the second thing is the longest thing at 100 things in it, so it's 0. So that's fine. So we can do this. We can do if diff is greater than 0. So if it's shorter, right? If it's shorter than our max len, then we need to do our padding. So how do we do padding? The easiest way is just physically add the padding on. So I know that my label here, so if we print sample, and let's actually throw a break in here so we don't print them all out. This is my sample, but I know it's 26 short of the longest thing. So why not just add 26 things to this? So what we're going to do is very simply create a padding oops, is equal to, it's going to be our special token dict at our pad token, right? So we're going to describe this pad token for blank in range diff. So all I've done is created, I keep doing this. I need to remember what I wrote for this. So this should be special tokens dict. It's plural. Okay. Okay, special tokens dict. All I've done is created a padding of, or basically a list of our pad tokens. In this case, the pad token was just one. So I've created a list of 26 ones here. And all I need to do is concatenate this onto my original data. So we can do our sample is torch.concatenate between our sample and the padding that I just created. So now if we look at our sample, we can see that, and I think I need to provide the axis. Looks like, oh yes, so this can't be a list. This needs to be a torch.tensor. Otherwise it doesn't make any sense. There we go. So I had my original data, right, with the end token, right, end of sentence token, but then I added all this extra padding information in because I need to pad my shorter sentences to the longest thing in the batch. So there you go. There's my pad tokens. And by default, this RoBERTa uses 1 as its pad token, right? The index for its pad token. Now that we have that, we can go ahead and replace in our token samples, right? In our token samples, we can replace it with our new sample. So all I've done is take the original sample that wasn't padded and in index and just replace it with the new sample that has been padded. So this goes ahead and takes care of our sample. But if we add a bunch of padding to our sample, we also need to add padding to our label. And by default, we don't want to compute loss on these things, right? There's no masking, there's nothing happening here. This is all pad token, which means we just need to concatenate -100 onto our label. So if we print label, you'll see this is what we have, but this was only for, you know, the data that we had, right? The sequence that we had. This does not include any of those pad tokens. So if we added 26 pad tokens to our original sequence, we should also add 26 -100s to this sequence. And -100 because we have no interest in computing loss on these pad tokens. And it doesn't make sense, right? There's no masking strategy happening within this extra pad information anyway. So these would be -100. There's nothing else to put there. So cross entropy will just ignore them, right? We don't care about them. So we can do label padding is going to be equal to just torch.tensor. And all I want is -100 for blank in range diff, right? So I'm just going to create a list here. And there we go, print label padding. It's just a list of -100s. It's a tensor. And all I can do then is just do my label. Label is equal to torch.concatenate. And we're just going to concatenate on our label. And we're going to just add the label padding to it, right? Just filling out the batch. So print label. I keep spelling label wrong. So let's fix that. There we go. So I've added all these extra -100s here to fill out the batch on our labels as well. And there we go. Now that we have our labels done, we can then, again, just like before, label samples index is equal to label, right? We're just going to replace it out. Label samples index. Yep. And we rinse and repeat this. So there's one more thing to do. We need to compute our padding mask. And so the padding mask is just going to be wherever our sample is equal to our special token dict tokens, tokens dict pad. There we go. So this padding mask is just going to tell me, if we print it out, it'll make sense. Padding mask. What's wrong this time? Wow, I feel like I spelled this wrong every single time I've typed this. Should have picked an easier name. So this tells me where are my pad tokens? And as you can see, they're right here, right? Now this looks backwards from what we did. In the attention is all you need implementation, we had true where we wanted to compute attention and false where we didn't want to compute attention. So just to try to keep us in the same spirit of things, I'm going to do not equal to. So this will be true everywhere where we do want to compute attention, or basically our non-pad tokens, and then false where we don't want to compute attention. These are our pad tokens, right? So there we go. That's our padding mask. And I'm just going to go ahead and store inside our padding masks .append. Oops. There we go. Append padding mask. Now that we have all that, we can go ahead and wrap it up. We can do token samples is equal to torch.stack token samples. Right, so I'm just taking my data and just stacking it together to create my batch. That's my token samples. Label samples is equal to torch.stack label samples. And then our padding mask is equal to torch.stack padding masks. There we go. Token samples, for example. Right, so I've batched my data. We can do .shape, for example. There should only be 2 samples, I think. So we get a 2 by 100. So the shorter things were all padded to 100. And there we go. We now have all of our data ready to go. And I just like typically writing this as a dictionary, basically returning like a dictionary. So we're going to do input IDs is going to be our token samples. Our labels is going to be our label samples. And then finally, our attention mask is going to be the padding mask. And there we go. We now have a full data collation function to do everything we want, and we can return the batch. And so this means we can print the sample right here. And you can see we have our input IDs, that's our input data. We have their corresponding labels, and we have their corresponding attention mask, right? Where do we want to put attention? Where do we not want to put attention? So on and so forth. So I think this is correct, unless I'm missing something. Let's check something real quick. I might be missing something. I am actually missing something. So yes, this is only if diff is greater than 0. What if it's not? What if it is 0? Like what if I'm on the longest sample? So we can do else padding masks dot append torch.ones, and then we can convert this. It should be self.max length. So if we are equal to the maximum length, like if we're on the sample that's the largest sample in the batch, then we don't have to do any of this padding stuff. So that's all gone because everything's already at the maximum length. And in our attention mask, we want to attend to everything. So that's true for everything. So that's why it's torch.ones. And then what I'm going to do is make sure that our padding mask is a Boolean. And there we go. So self.max len. Okay, what's the matter? Name self is not defined. Right, there is no self. This would be the just max line, not self.maxLen. My bad. Okay, and there we go. Now we have it. So we have created our tensor. It looks like it's missing something. Padding masks. So let's just do a quick print len padding masks. It's 2. When I stacked it together, it looks like it just created one big tensor rather than 2 of them. So let's check here. Print padding masks dot shape. Oh no, it's correct. I guess I'm just missing the. There must be something I'm missing. It's fine. Yeah. Okay. We're good. All right. And we can again just check here real quick. We call it attention mask dot shape. Oh no, this is a oh yes, padding masks plural. There we go. All right, there we go. That fixed it. So now we can do a batch size of whatever we want, like 64, and everything will just work fine. And it's been, you know, all this information is ready. We have our data, we have our corresponding labels where everything is -100, where we don't want to compute attention or compute our loss, and then we have our attention mask, identifying where we want to compute attention, where do we not want to compute attention. And this is it, by the way. This is basically all the novelty of RoBERTa, BERT, that sort of stuff. There's nothing else to do. Everything I'm going to do now, I'm going to go through in some detail, but not too much. If you want basically like the details of, oh, how do you do padding masks and the attention mechanism and stuff like that, I recommend, again, just going and looking at one of my previous videos when we did the deep dive in attention, and that'll give you all the necessary context you need to understand exactly what's going on. I will do it a little bit more hand-wavy today just because I've already done it before, right? So I don't want to do it again in that much detail. Just go watch the previous videos for that. So we're going to do class SelfAttention and then dot module. Great, and our self-attention is the same as always. So we have a self. We have our embed It's going to be 768 and a default transformer. The number of heads of attention we typically do is 12. And then our attention P, we're going to set it to 0. And our proj P, projection P, we're also going to set to 0. Okay, so those are our dropout probabilities. And I'm going to create or copy some data in. And I actually call this self-attention encoder because this is a encoder attention. Not that it really matters, but just so it's clear, encoder. And I'm just going to copy this little chunk here just so we can see what's happening. So what I've done is generated some random tensors here. And I've also said that these are my padding masks, right? But in my case, I actually do it backwards because I want it to match all of our previous implementations. So I'm going to just set this to, actually, let's just do everything is true on the first one. And then like the first 3 things is true on the second one. There we go. So in my sequence of 5 tokens, in the first sample, all 5 tokens we want to compute attention on. In the second sample, we only want attention on the first 3 tokens, and we want to ignore attention on the last 2 tokens. So again, you should be familiar with this stuff right here. How do we do the attention masking? Why do we fill in negative infinities in the column? And how that kind of all works out. Again, if you need extra details on this, I have an entire video series just dedicated to exploring this, right? The details of this. So again, I'll just link it down below, but that is the prerequisite for this. So I'm not going to go into much detail of the why and just kind of implement it and have it. So let's go ahead and do it. So we're going to do self.numHeads is numHeads, self.embeddIm is our embeddIm, and our self.headDim is going to be the self.embeddIm integer division by the self.numHeads, right? So there we go. That's our embedding dimension per sample. And what we're going to do now is do our self.q is nn.linear. It's going to have embeddIm input, embeddIm output, and our QKV are all the same, right? So Q, K, V, and we'll have our final projection as at the end as well. So Q, K, V, and our projection, right? And then our self.attention drop is going to be nn.dropout, and it's going to be with the attention P, so whatever probability we specify there. And then our self.proj drop is going to be, again, nn.dropout, or in this case, it'll be proj P. And there's all the layers that we need. And so we now can do def forward self x input, and then our optional attention mask, right? If we have an attention mask, by default it's none, but we're going to put it in there. So our batch size by sequence length by embeddIm is just x.shape, right? That's the shape that our data will come in. And so we can now do q is self.q, and we're going to pass in x. And k is self.k on our x, and v is self.v on our x. So these are our 3 projections of our original data to produce our queries, keys, and values. But just like we saw before when we did like our efficient attention implementation, all right, I forgot my super.init. Okay, and out.shape, because we actually don't have an output yet, so there is no, it's none type. That's fine. So if we print q.shape, right, we have batch size by sequence length by embed dim. And let's say our num heads, I did num heads is 4. So that means each head of attention will have an embedding dim of 4. So let's actually do 2 just to make the numbers different. Good. And I'll make the batch size 3 just so the numbers are a little different. So we have 3 samples. Each sample is a length of 5. Actually, that won't work. Let's just put it back to 2. We have 2 samples. Each sample is a length of 5. And the embedding dim of each token is 16. And what I want is 2 heads. So that means really, instead of a single embedding dim of 16, I have 2 different embedding dimensions of 8, right? So we're doing our, basically our disentanglement of these embeddings. So we're going to do Q, and we're going to take this last dimension and just split it up. So we're going to do dot reshape, batch size by sequence length by our, instead of just embed dim, it's going to be self dot num heads by self dot head dim. And there we go. So all I've done is taken my tensor and split it up. So we have 2 heads. Each head is a dimension of 8. And I want to compute my attention computation in parallel along the batch and the heads. But unfortunately, my heads is here right now, so I need to permute or transpose these 2 dimensions. So we can do dot transpose 1, 2. Right? So we have a batch. Each sample in the batch has 2 heads, and each head, it has a sequence length of 5 with an embedding dim of 8. So there we go. That sets up our attention. And we do that for all of them, right? Q, K, and B. And so now our attention is going to be Q at K transpose, right? Transpose 1, 2. Because we have a 2 by 2, so we can ignore that, right? These are the dimensions we're going to parallelize over. So Q is a sequence 5 by embed dim 8. And K is transpose, so we have to do 8 by 5. So we want to flip these 2 dimensions, right? The last 2. So that's actually be -2, -1. So we want to flip these last 2 dimensions. And then we just want to multiply by the scale. So we can do times self.headDim to the power -0.5. Right? So there we go. That'll do it. So we want to divide by the square root of the head dim. Well, here you go. We're dividing by the square root of the head dim. And that gives us our attention computation. Once we have attention, we can print it out. Print attention.shape. There you go, right? So we have 2 by 2. So we have 2 samples. Each sample has 2 heads. And then we have a 5 by 5 attention matrix. But now it's time for us to do our attention mask, if it exists. So if attention mask is not none, right? If the attention mask is not none, then we want to replace the columns that are false with negative infinity. Basically this, right? So if we have a pad token at the end, we want in our attention mask, if let's say we had 3 tokens and the first 2 tokens are actual numbers and the third token was a pad token, then in our 3 by 3 attention matrix, we want the last column to be filled with negative infinity. So when we actually go to take the softmax, it becomes a column of zeros and everything else is normalized to 1. So let's go ahead and do that. So if our attention mask is not none, what we can do is, well, we actually have a little bit of work ahead of us. So we can do attention mask.shape and our attention.shape. So we can see that our attention mask is a 2 by 5, batch by sequence, but our attention is 2 by 2 by 5 by 5. So batch by heads by sequence by sequence. So we need to add in these 2 dimensions in the middle as kind of a filler, right? So we can do attention mask. This is just so we can broadcast, right? So attention mask dot unsqueeze 1. If we do it once, we see now we have a 2 by 1 by 5. And so let's just do it a second time, right? So we do it a second time, and now we have a 2 by 1 by 1 by 5. And that is our broadcasting operation, right? It lines everything up. And so now that everything's lined up, we can directly go ahead and use attention equals attention dot masked fill. We want to fill with this attention mask, and we want to fill with float negative infinity, right? And as we know, the attention mask is actually flipped, so we have it as true on the, well, actually it's probably easiest just to see what happens rather than explain. See how it did it backwards? It put negative infinity everywhere except on the tokens we actually wanted to do it on, right? Because it's going to put negative infinity where it's true and then leave everything else alone where it's false. We want it backwards. So all we need to do is add our Boolean flip operator, and there you go, right? We fill these with negative infinity, everything else is good to go. And that's our attention mask being applied. Now that we have our attention mask, we can now go ahead and do our softmax, right? So attention is attention.softmax, dim equals -1. So there's our softmax. And then finally, we need to do our attention is self.attention drop, attention or dropout. And actually, it'd be good to see print attention. When we do the softmax, notice the columns that are pad tokens are set to 0. Basically, we make them 0. And they're 0 because we want to make sure when we multiply by the values, these pad tokens have no weight. They don't mean anything. They don't add any context. We just added them as fillers. So this just makes sure they're 0. So now we have our self.attention dropout. That's fine. And lastly, we can do x is equal to our attention at v. So that's our qk transpose, divide by the embedding dim, square root of the embedding dim, softmax it, and then multiply by v, and that's our full attention formula. So if you do print x.shape, you'll see this 2 by 2 by 5a, batch by heads by sequence length by embed dim. Now it's time to put it back. So we did a transpose here, so we need to do another transpose, and then we basically separated out the dimensions here. We need to put them back together. So let's just go in reverse just to put ourselves back where we started. X is equal to x.transpose 1, 2. I should actually left this here. So that'll flip these two around, right? So now we're at 5, 2, batch by sequence by head by embed dim, and we can flatten these last two dimensions. So dot flatten 2 in this case. Right, so that flattens it, and we're back to where we started. But remember, the heads were all parallelized over, so the different heads haven't had an opportunity to communicate. And so now's the time to do that. We can do x is equal to self.proj x, and then x equals self.proj drop x for the dropout. Right, so the projection will get all the heads to get to know each other. We will do the dropout to help with overfitting if necessary, and then we return x. And we are done. That is our self-attention encoder. This should look very familiar to the attention implementation we've already seen in the past. So again, this was just a very quick little kind of, go through of it. If you want the more kind of nitty-gritty details of like why did we do the mask and all the other information, just go take a look at one of my older videos where I talked about attention in detail. And again, I'll link it down below. So now that we have that, again, this is assuming you've already implemented a transformer before, right? So you know the kind of the bits and pieces that go into a transformer. All we need to do is implement the rest of it. So all we've done so far, and again, we are ignoring this right chunk. We don't care about any of it. We need to implement the feed forward module and this add and norm residual connection. But we've already implemented this orange box. That was the multi-head attention we just did. So let's wrap it all up to create our transformer block. And then we will wrap that in our overall ResNet the RoBERTa architecture. So let's go ahead and do that. So let's, first we're going to do our feed forward or MLP. So MLP, multi-layer perceptron, nn.module, def init, and we're going to do self in features, hidden features, and then out features, and then MLPP equals 0. Right, so there we go. So all we need is, if you remember again from our, not there, let's look. Oops, I closed it. Attention is all you need right here. So if you again remember in our feed forward layers, it's basically just a linear layer with an activation function. They use ReLU. And then another linear layer. But today we actually use GLU instead. GLU seems to be a much better activation for transformers, so that's what we're going with. So what we want to take a look at is, first we're going to do self.fc1 is nn.linear. It's going to go from in features to our kind of intermediate hidden features. And then self.activation is going to be nn.GLU. I think it's all uppercase, so GLU. That's our activation function. And then self.drop is going to be nn.dropout on our with MLPP as our dropout probability. And then we simply have self.fc2 is nn.linear. It's going to now go from hidden features back down to in features. So there we go. And then we have actually this should be drop 1, and then self.drop 2. So again, nn.dropout mlp p. There you go. So those are my 2 layers, 2 dropouts, and my activation function. So def forward, self, x, and very simply, x is equal to self.fc1 x. X is self.activation function x. X is self.drop1x. X is self.fully connected 2x. And then x is again self.drop2x. And we return x. That's it, right? I'm just passing my data through all of these different layers and nothing else. That's my multi-layer perceptron, nothing crazy. And so now it's time to make the transformer block. So class block. This is just going to wrap our multi-layer perceptron and the attention module together, but it's going to do it for with the residual connections as well. And I also need the super.init here. There we go. Init self. Embedding is again, like I mentioned, 768. Our num heads is 12. Our MLP ratio is 4. And the MLP ratio, if you don't remember, is basically our input features is 768. Our hidden features is going to be the embedding 768 times the MLP ratio 4. So it's basically our, our scaling factor for the hidden layers, for the linear layers. So now we have our MLP ratio. Our proj p is going to be 0 by default. Our attention probability, dropout probability is also 0, and our multi-layer perceptron probability is also 0, just set by default. And we're good there. And so if you remember again, for super.init, if you remember again, when we do transformers in the implementation, you can see there is a add and norm. So we also need the norm, the normalization. And the normalization is our, it is our layer normalization that we use, because batch norm would be across multiple GPUs, and it's just not really practical for transformer training. So we're doing layer normalization. So we're going to do self.norm1 is going to be let's fix that. Yeah, self.norm1 is going to be nn.layer norm. And we just need to provide layer norm the embed dim, right? What to expect. So embed dim. There you go. And then we have self.attention, right? So that's going to be our self-attention encoder. And this is going to get the embed dim, our num heads, the attention p, and then our proj p, right? So that's all the arguments for a self-attention encoder. And then we have another normalization, right? So there's 2 added norms. So again, layer norm, embed dim. And once again, we're going to do self.mlp, multi-layer perceptron, will just be our multi-layer perceptron with in features being our embed dim, the hidden features being embed dim times MLP ratio. And we'll just make sure this is an integer when we do that multiplication. There we go. And then our out features, again, will be embed dim. So that's what we're going to come back to. So it's all the same. And I think the MLP dim and then the MLP P is just our MLPP. So there we go. Yep. Yeah. Okay, good. So we have everything we need. And just like before, forward, self, x, and also its corresponding attention mask if available, right? If it's there. So just like before, x is equal to x plus, that's a residual connection. So we're going to add 2x. We're first going to pass x through the norm. So norm 1x, we're going to normalize x. And then we're going to pass it through our transformer, so the attention mechanism. So we're going to pass it through attention. But when we do pass it through attention, it can get the corresponding attention mask. So that's, again, what we implemented, right? We passed in x and the attention mask. So there we go. We passed in our normalized x and the attention mask. And we added it to itself to provide the residual connection. Again, x equals x plus self dot MLP P, and we're gonna MLP, and we're gonna apply this multi-layer perceptron onto normalized x, right? So we're gonna normalize x, pass it through the multi-layer perceptron, add it to itself, and there we go. And now we can go ahead and return x. And that is the completion of our block. And this block is what we're now going to use in our transformer. Now, to do the transformer, there's one thing I want to talk about, and this is known as the CLS token. Now, we technically don't need the CLS token right now, but we are going to just toss it in there. Because if you're fine-tuning your model, then you'd actually need it. And here's the idea. We've seen in the RNN examples, right? There's actually different types of RNNs. When you do like sequence problems, there's like aligned sequences and there's like offset sequences and so on and so forth. But the main idea is this. I'm passing in a sequence of tokens, token 1, token 2, token 3, ... token n, right? And I'm passing all of this into a transformer model, right? Former model. That means the output, so if this is all the inputs, so there we go. That means the output is going to be context vector 1, right? And we talked about this. This context vector is how T1 was related to all the other things, like the relationship between T1 and all the other tokens. We'll have context 2, how T2 was related to all the other things. Context 3, ... Again, we'll have a context n. And now the question is, I want to predict, right? Let's say we're doing sentiment analysis. So we have happy versus sad, right? That's my classification task. The problem is I have so many outputs. Which one do I use? Well, you could just use the last one. So that's what we do in the RNN, right? In the RNN example, we just grab the last value and use that as is. And that would probably work out fine. But that's typically not how we do it in transformers. There's two things we can do. One, pooling. So these context vectors is how every token is related to every other token, right? And so what we can do is just take all of these things, average them together, and just have a pooled context vector. So C will just be the average of C1 through Cn. So that's option 1. And this will work just fine. And a lot of the Hugging Face models are implemented like that. Number 2 is CLS token. So this is what I want you to keep in mind. When we pool or just directly take an average here, that is me saying every single word is equally important. So if there's 10 words, then I'm multiplying everything by 1/10 and adding them together. So they all have equal importance. But what if I want to have a weighted average, like maybe C3? Maybe there's specific words that are more important about telling you happy versus sad than other ones, right? Like if you're doing, oh, this is the greatest movie ever, the word greatest would probably have more importance than this in the, some of the filler words in the sentence. So if we want to do a CLS token, we can actually use something known as the CLS token. This is basically a weighted average, right? So what we're going to do is create a special CLS token, and we're just going to pass it into our model along with all the other tokens, right? It's going to go in with all the other tokens, just like before, and it's going to produce a context CLS. And remember, attention, when we do the attention computation, right? So if we do attention, let's say we have the CLS token is first, and then you have token 1, token 2, token 3. So the CLS token is first, and then token 1, token 2, token 3. We learn how is 1 related to CLS? How's 1 related to 1? 1 related to 2, 1 related to 3. And then how are everything related to each other? And this is all well and good. We're learning the interrelationships between the words. But the most important is how is the CLS related to 1? And itself, obviously, but that doesn't really matter to us. How's CLS related to 1? How's CLS related to 2? How's CLS related to 3? And these will end up being the weights. So CLS token ends up being a weighted average of itself and all the other tokens in the sentence. So this is basically a weighted average, right? Weighted average of all tokens. And so when we go to predict, all we can do is, let's say we're done. Method 1 again was we can take all of this and pool and send to a classifier, right? A linear classifier head. So we can pass that to a classifier. Or we can just slice this piece off and just send that to the classifier. So by pooling, we're saying that all the tokens are of equal importance, and that's it, right? We pass it to the classifier. By using the CLS token only, we now have a weighted average of all the other context vectors, right? Because it's separated from the context vectors. This is just a weighted average of all the context vectors that we can then pass to the classifier. So we can construct the CLS token as a learnable parameter right at the beginning of training, and you'll see that in just a moment here. So that's the main idea. I wanted to get that across. This CLS token is important. It shows up in a lot of places. It'll show up again in the vision transformer for exactly the same reason. So we'll see it then again, and I'll explain it again at that time, kind of in the context of vision of why it would matter. But yeah, the main idea is some words may be more important than other words to do this classification task. So by just doing a regular pool, you are not incentivizing or basically putting more emphasis on some words over the other. So the CLS token can learn the weighting between itself and all the other words to ensure it puts more emphasis on the words that actually, identify happy versus sad. You'll probably get very similar results regardless of the method you use. So this shouldn't be like a turning point, but there is I can't remember exactly where, but there was a paper I saw before where they saw that the CLS token seems to scale better for larger data sets and for larger models. So your best bet's just going with the CLS token. In our case, though, what we're working on right now, we're not going to use the CLS token. We are only doing the training of our masked language modeling, right? MLM. We would only need the CLS token if we were doing downstream classification, which we aren't doing right now. So for all simplicity, I can actually probably just not include it for now, right? If we're not really using it, then I'm not going to include it. I just wanted to mention it. We will include it when we do the full RoBERTa implementation coming up soon, just because we want to be able to do fine-tuning tasks with them. But today I just want to keep it simple, so we're not going to include any of the CLS token stuff. So let's go ahead and do class RoBERTa, right? So RoBERTa, nn.module, def init, self, and we just need all the information. Max sequence length, what's the maximum sequence length we want, the vocab size, how many possible tokens can you pick from? That's just dependent on our tokenizer, right? So tokenizer.vocab size. Then we have our embed dim, right? So again, we're going to do a 768 embedding dimension. Our depth is 12. We're not actually going to train such a big model today. We're going to train a much smaller version of it. But yeah, this should just give you an idea. So now we have our depth. We can then go ahead and do num heads. This is going to be 12. MLP ratio was 4. And then our attention probability dropout is 0. Our MLP probability dropout was again 0. And the proj dropout is again 0. And finally, we will have our positional embeddings. These are going to be 0. So we actually haven't talked about positional embeddings in much detail yet, so now is a time to do that. Let's just go ahead and do super.init. Good. And let's go ahead and start our, let's start this. Actually, I will just go ahead and add the CLS token in because even though it doesn't matter, it'll match my implementation online, and I want to make sure there's not too many discrepancies between what I have on my Git repo and what I'm kind of showing y'all on YouTube. So we'll add it in, but we're not going to really use it for anything today. It'll just be there. So we're going to store self.max sequence length is our max sequence length. So there we go. Our self dot, so first embeddings, right? So we need to convert our tokens to embeddings. So self.embeddings is going to be equal to our nn.embedding. It's going to, uppercase E, embedding. And it's going to be our vocab size by our embed dim, right? So how many words do we have and how many numbers do we want to use to represent every word or tokens? Now we have our CLS token. So I'm going to create self.cls token. And all we're going to do is just randomly initialize it. For now, I'm just going to do torch.zeros and just leave it as is. We're not going to care about the CLS token. So you'll see how we apply this in just a second. But basically what we've done is define a parameter, which we've seen before, right? So these are basically just like weights and everything else, it's just another set of parameters in the model. That's it. And by default, these will require grad. And the reason we're using parameters, so when we move the model to the GPU, the CLS token also moves to the GPU alongside with it. And we're initializing them as just a bunch of zeros because we don't really care about them right now and we won't use them for anything right now. So that's fine. We can just leave it alone. And the reason I did 1, 1 embed dim is because we have, we want to broadcast over the batch dimension and we want to concatenate on the sequence dimension, and you'll see exactly what that means in a bit. So we have our embeddings. Now we have our positional embedding, pause embed. So this part will be a little bit new. If you remember, when we looked at the Attention is All You Need paper, they mentioned in this section here about positional encoding. So we implemented the sine cosine embedding last time, and this will work out just fine, right? So just go ahead and use the sine cosine instead, and it'll probably give you very similar results. So that's fine. The thing is that they also experimented with a learned positional embedding instead, right? And they found that the two versions produced nearly identical results. The benefit of sine cosine embeddings is because they're not learnable parameters, you can technically just interpolate them to be a longer sequence, right? You can just interpolate and make more samples and just stretch out the sine cosine embeddings. We can't do that on a learned positional embedding, but for now it's fine. So we're going to go with it. So we're going to use a learned positional embedding. So let's go ahead and do that. If you remember again, the reason we need positional embeddings in our neural networks is because we need to add positional information because transformers are permutation invariant. So what we have is, let's say, data, which is going to be some sequence length by embedding dim. And we're going to have our positional embeddings here, positional embeddings. And this is going to be our max len by our embedding dim. And all we need to do is just clip off the piece that we need, like this much right here, and then add these two things together. In this case, what we're going to do is initialize our positional embeddings as a, as a learnable matrix. And again, if we just need a matrix of numbers that's something by something, we could use nn.parameter. We can also just use nn.embedding, right? So let's just do that. And you'll see why we do that in a bit. nn.embedding. This is going to be max sequence len. And we're going to do max sequence len plus 1 because we're actually going to be adding a CLS token onto it. So you'll see that in a bit. So plus 1. And then our embed dim. Right, so now we have our embedding, CLS token, positional embedding. All we have left is self.positional dropout, pause drop. And this is basically a dropout on these positional embeddings. So nn.dropout, just like before, drop out, pause, p. There we go. Now we need the actual transformer. These are the blocks. So we're going to do self.blocks. Blocks is going to be nn.module list. So we've done this before. And we just need to do our block. And I'm just going to copy this in so I don't have to type all this out. But it's exactly what you think. It's just our blocks, right? So we're going to grab our block and just repeat them however many layers we want. So 12 times in this case. That's our block. And then we'll have a self.norm is nn.layer norm. And in our layer norm, we're just going to provide it the embed dim. There we go. And then we'll have our self.head is nn.linear. And again, the question is, we saw this before. We want to classify, right, our classifier. Here we go. We want to predict, like, what is the token? Like, is it token 2, token 3? But this is one of our however many tokens are in our data set. So, for example, we have like token 1, token 2, token 3. We mask out token 2, and we want to predict what is the token. So you have your list of tokens, right? You have token A, token B, token C, dot, dot, dot. Like the list of all the possible vocabulary that we have. And so we just need to know which token, which one of these are there. So our linear layer needs to predict an output of however many unique tokens are in our specific model. And so we can go ahead and do that too. So this is going to have an input of embed_dim and an output of our vocab size. And there we go. And so all we need to do now is just write the forward function and we are done. So self.forward, def forward, self x and attention mask is none by default. And just like always, we're just going to go ahead and do what we put everything together. So we're going to first store here. We're going to need this in a bit. So we're going to see x.device. We're just going to store the device on which we're training. So in this case, you know, if it's on CUDA, which GPU is it on? Is it on CPU? Hopefully you're not training on a CPU, but there we go. What device are we on? And what we're going to do is if sequence len greater than self.max sequence len. This won't happen because we've already gone ahead and clipped our data, right, to the max sequence len. But if you're inferencing, right, it could happen. If our sequence len is longer than the max sequence len, then we're just going to go ahead and make sure we clip off all those samples. So we're going to say negative self.max sequence len to the end. So we're just going to grab the last bit of the text. Again, this won't really apply to us, but it could happen if you're inferencing. So there we go. Or you could grab the first like 0 to max sequence. It's up to you. It doesn't really matter, I feel like. Okay, good. And what I'm going to do is just grab this dummy data, this testing data that I have here. Looks like I have a bug. Oh, right. I don't have any of these because I got rid of those. So we're going to get rid of that. And now we have layer norm. Shouldn't just be layer norm. It should be nn.layer norm. Let's see here. So I have it there. This is complaining about my multi-layer perceptron. So here, nn.layer norm. Okay. Okay, good. Still have another bug. Oh, if sequence len. So, right, I didn't actually do that. We're also going to do batch size by sequence len by embed_dim is our x.shape, right? That's the shape of our data. Okay. And not enough values to unpack because we actually haven't encoded our text yet. So it's just batch by sequence right now. And yes, this will throw an error because we haven't done that yet. So there we go. That's everything. Currently, X is still tokens. We haven't converted them to embedding, so it's just batch by sequence len. And we're just clipping off any extra tokens if we had any extra, but we don't, so we're fine. And just like I had before, I'm going to make all of these true. Oh. Let's make all of these true, true, true. And then we're going to make all of these true, true, oh. True. Oh, why does that keep happening? Sorry. My bad. Sorry, mouse was being weird. True. True. And we're just going to say the last one's false, right? So there we go. Something like that. And so we've gone ahead. We're going to first pass an X just like we did. And now what we're going to do is figure out our available indexes. So we're going to do avail index. It's just going to be torch.arange from 0 to sequence len plus 1 because we're going to be adding that our thing in a bit. We're going to be adding in our CLS token in just a bit. So whatever our sequence length is here, our true sequence length is going to be this sequence length plus that one CLS token that'll show up soon. And we just want to make sure the D type of this, right? We're going to make sure this is a torch.long tensor because our embeddings, when we actually pass data to the embedding, it expects a long tensor. So there we go, torch.long. And our device is device. So we print avail index. It'll just look something like this. So we have 5 tokens in this case. We created 2 by 5. So there's 5 samples in this thing, or sequence length of 5. So it goes from 0 to 4. But we get this extra 5 because we have that extra CLS token. So there we go. That's our avail index. So we can now go ahead and just index our embeddings, right? These embeddings, these positional embeddings are the same as before. So first up, we are going to convert our tokens to embeddings. So we're going to do token embed emb. It's going to be self.embeddings x. So print token embed dot shape. And it'll be exactly what you think, right? So 2 by 5 by 768, I grabbed my numbers that represent each of these tokens. So there we go. We started with a 2 by 5, right? We started with a 2 by 5, 2 by 5, 768. Now I want to add the positional embeddings for the first 5 tokens, right? The first 5 things, or 6 things in this case. So before we do that, we need to concatenate on our CLS token. How do we do that? We can do CLS token. We can create a copy of it. It's self.cls token dot expand. We're going to repeat it batch. So remember, it's 1 by embeddim. What I want to do is repeat the CLS token batch size number of times. So it'll become batch size by 1 by embeddim. So batch size by 1 by, or actually, and we'll leave all these other ones alone. We won't do anything with them. So there we go. So if we print out the CLS token dot shape, you should see that it becomes, we had 2 samples in our batch. So 2 by 1 by 768. And now I can concatenate it on. I can do toke embed is going to be torch.cat or concatenate. And we want to concatenate the CLS token onto the token embed. So I could concatenate it onto the beginning. I could concatenate it onto the end. It doesn't matter. You can do it wherever you want. The transformer won't really care. Dim equals 1, right? We want to concatenate it on the sequence dimension. So if we print toke embed now dot shape, what you'll see is that it is a 2 by 6 by 768, where the first token is a CLS token, and then the next 5 tokens are the actual data, the thing that we had. So we've just prepended our data with the CLS token, which should remind you of BERT, right? So that's kind of this picture here, right? They prepended all of their tokens with this CLS token. And we're going to see this over and over again as we start implementing more and more architectures in the future. Now that we have our CLS token done, right? We've added that in. It's time to add our positional embeddings. So let's grab, so we have 6 positions here, right? So positions 0 through 5. So we just need to grab embeddings 0 through 5 in our positional embeddings, right? That's all it is. So again, if we look at our picture, our positional embeddings goes from 0 to the maximum length, but we only need the first like 5 of them. So we're just going to index out the piece that we need and then add them together. And to index them, that's why we created this avail index right here. Right? This is going to go from 0 to 5 or whatever it is, 0 to 6, and it'll index them out and create that. And so now we just have to index it, so we can do our pause embed is going to be self.pause embed. So I think of what I called it, pause embed. And we're just going to index it with our avail index, print pause embed dot shape. And there we go. These are my 6 positional embeddings, just grabbing them from my embedding matrix. And like I mentioned, these are trainable parameters. Instead of sine, cosine like we did before, these positional embeddings will train to be the best positional embeddings that they can be. This is not totally recommended today. There's better embedding methods out there like rotary embeddings and whatnot. We'll see those in the future, but this seems to work fine for what we're trying to do. So we're going to leave it as is. Now that we have our positional embeddings, we just need to add them onto our data. So we can do X is going to be our token embeddings, token embed, EMB plus pause embed, right? Me adding my positional information to my data. And now that all that is done, we need to just add that dropout. So X equals self.pause drop. This helps ensure that we're not overfitting on any type of like our positional information. So there we go. And lastly, all we need to do is take our data and pass it through all the transformer blocks. So for block in self.blocks, we're going to do X equals block X. And finally, we need to do our mass prediction. So we're going to print x.shape. We're going to let it run through. Let's see what our bugs are. So not enough values to unpack right here. That's weird. So let's double check our x. Print x.shape up here. Okay. So looks like something has gone wrong. So what I want to do first is print toke embed.shape up here. Okay, that had the batch size, so that's good. And if we print x.shape right here, it looks like we still have that 2x6, so that's good. But then when we print out x.shape right here, is it still correct? Becomes 6x7, 68. What could have gone wrong? Our pause drop is just a dropout layer. Oh, of course. We need to apply this on x, right? So there we go. There we go. So we've passed it through all the transformers. We get a 2x6x7, 68. But again, remember, we want to do the masked language modeling prediction. So what we have right now is we've passed all this information in, and we know that our data is already pre-masked because we spent all that time doing all that masking logic. In this case, right, when we pass stuff in, we've now added this special CLS token at the beginning of the sentence, right, before all this other stuff. We don't need this, right? This doesn't matter for our masking logic. So we're just going to cut out the CLS token and then keep going. Like I mentioned, we don't really use the CLS token for anything today. So it's just kind of there as a filler, but we don't need it. So we're going to do x. X is equal to x. We're going to grab everything from 1 to n, right? Because we don't need the CLS token, which is the first thing that we appended on. And so then x is equal to self.head x, and we can return x. Right, there we go. And we can now finally print out.shape. Oh, okay. And we can see we have 2 samples. Each sample is a sequence under 5. And for each sample, we have, we're predicting 50,265 possible things that could be there. And that's it, right? That's the entire RoBERTa implementation. The implementation we're going to do later is a much more beefed up version of this. It'll just be better and it'll have good weight initialization and all that sort of stuff. But for now, let's just go ahead and do the rest of this. So now it'll be quick. So we can do iterations. I want to train for, let's say, 15,000 iterations. There we go. Max len, I'm going to say is 100. Our evaluate interval, let's say, is every 100 we'll evaluate, and embeddim is going to be 384. Our depth is going to be 4. Num heads is going to be 4. And our learning rate is going to be 0.0005. Just picking random stuff here. And then our batch size is going to be 64. And we're going to say our device is going to be CUDA if torch.cuda.isAvailable else CPU, right? So there we go. And so we can just define our model like this. I'll just copy paste some parts of this. Actually, I'll copy paste a bunch of this because none of this is new to y'all anyway if you have done the prerequisites. So we have our device, we have our model, right? I added some of the dropouts here. So there you go, 10% dropout. So that's our model. We can print the model out here, print model. We can move the model to the device. We have our optimizer. We have our loss function, right? And then we just go ahead and take the data set that we wrote, the masked LM loader, everything that we worked on. I go ahead and just split it into a training and testing split. So 95% for training, 5% for testing, whatever. And then we create our data loaders around that using the collate function that we wrote. And I just write we're using a scheduler, and this is the Hugging Face. We just use their cosine scheduler, so that's fine. Nothing crazy. And so let's go ahead and write a quick training script. So that needs to be embed dim. There we go. That's what our model looks like. It looks like I'm missing an import actually, so let's add that in. import torch.optim as optim. There we go. Yeah, so there we go. There's our model. Nothing crazy, right? Should look very familiar to previous models we've written. Let's go ahead and write our training script. So we're going to train is true. Completed steps, let's say, is 0. Our all training losses, all validation losses is going to be 2 empty lists. And then we're going to do training losses, and validation losses is, again, 2 more lists. This is where we're going to store the overall summary of the model. This is going to be for every evaluation interval, right? So we'll see that in a bit. And then we're going to do a progress bar, right? Good to see how things are going. Is TQDM range iterations, just like that. So we're going to do while train. So while we're training, we're going to do for batch in train loader, right? So we're going to grab batches at a time. And we're going to do inputs labels mask is going to be batch input IDs, right? So we're going to grab the input IDs, our batch labels, and batch attention mask, right? So all the stuff that we wrote. And then we just need to make sure everything's on the GPU. So we can do inputs, labels, mask is going to be, or inputs, labels, mask is going to be inputs.to device, labels.to device, and then mask.to device. There we go. And so we now pass it through our model. Our predictions is going to be model input, and then the our inputs and mask, right? Our attention mask. So there we go. That's what we pass into our model. And then we simply calculate our loss function. Now the thing is, if we print our predictions dot shape, I'm gonna throw a break in here and then do a train equals false, so it ends. This is our output, 64 by 100 by 5265, right? So those are all my possibilities. Our labels, print labels dot shape, is going to be this, right? Which makes sense. So all I need to do is flatten these dimensions. So I can do actually predictions is equal to predictions dot flatten, or actually we can do dot reshape -1 by predictions dot shape shape -1, whatever, right? So it's a dumb way of doing it, but that works. So all we're doing is basically we have 64 samples in our batch, or 64 samples in our batch. Each sample is 100 tokens, and each token has 50,265 possibilities. In my answers, I have 64 samples in the batch. I have 100 tokens in each sample, and these have the correct answer. So which one of these is correct is inside here. So all we need to do is flatten it. So we can make this a 64 by times 100 by this, and then a 64 times 100 like there. So we can do, and then print label, or we can then do labels is equal to labels dot flatten. And we get this. So we have 6,400 tokens, each with these possibilities, and these are the correct answers. And this is how we typically look at cross entropy, right? This is how we normally use cross entropy. You can also do cross entropy without flattening. It actually accepts that, but we'll see that later. We don't need to worry about that for now. So we have our model. We have everything we need here. And so now we can go ahead and compute our loss. Is a loss, actually, good thing to check. Let's just print our labels. Lots of -100s because most things were not masked, right? 85% of our data was not masked. Well, it's only the 15% that we want to compute that loss on. So what we're going to do is labels, or our loss is going to be the loss function, which I think I defined somewhere, but I can't remember anymore. Yeah, I did. Yeah, right here, loss function. So we are going to do the loss function between our prediction and the labels. And by default, like we mentioned, it will ignore all the -100, so we won't ever compute loss on those. So now we can print our loss. Predictions. There's a loss. Just like that, right? So nothing crazy. And then, as good practice, we're going to do a And again, as good practice, what we're going to do is our training losses dot append. We're going to store in here our loss.item. Right, so there we go. We're going to store the loss for this specific forward pass, and then we're going to do loss.backward, computer gradients backward. We're going to do torch.nn.utils.clip grad norm, right? Just good practice to make sure your model doesn't have any exploding gradients. Parameters can happen at the beginning of training. We're going to make sure it's just normed to 1. There we go. And then we will update our model, optimizer.step, optimizer.0 grad, and we also have our scheduler.step. There we go. Right, so update our learning rate scheduler as well. And that's our very, very basic training loop. Once we've done that, we can say we have completed a step, right? Completed steps plus equals 1, and our progress bar dot update 1. And we can do a sanity check. If completed steps percent evaluate interval is 0, right? If we've completed enough steps, so I think every 100 steps or something like that, we're going to do an evaluation. Well, we can go ahead and do that. Most of this code is identical, so I'm just going to copy paste it in, and it'll be fine. So this is going to be like this, right? So with no grad, again, we're going to loop through our testing data, grab the data, grab our predictions, compute the loss, whatever. Everything is exactly the same. And then we're going to go ahead and average up our training and evaluation loss, print it out, see how it's going, store it, and then reset it. And then we'll basically be done. All that's left then is if completed steps greater than or equal to iterations, right? So once we've completed our iterations, then we can do train equals false and just break the loop. And that will exit this training. Let's see how this goes. And yeah, so it has already taken off, and this will train just fine. Now, again, watching a training loop is of less interest to y'all, so I'll just show you what these results look like at the end once it's done. So I'll be back in a bit. All right, so now that training is finally done, as you can see, the loss is going down. It's a good opportunity for us to just quickly check what the training curves look like. I'll just paste this in. And you can see, as it's training, as expected, we are beginning to overfit. So you can see the training curve going down and down and down. And this is expected, right? Like I mentioned, transformers need ridiculous amounts of data, much larger batch sizes, more computational resources, and this type of overfitting is pretty common to see on a data set as small as just a couple of Harry Potter books, right? So either way, what I am curious about is what does the masking look like? So can we actually try this model out? So this model on its own, and why we do pre-training fine-tuning, is basically we train a model to understand English so we can fine-tune it so it can do something with English, right? Like question answering, classification, that sort of stuff. This model is just a fill in the gap model, right? It doesn't know any better. So our question is like, how well can it fill in the gap? So what we're gonna do is just write a function for that. So we're going to do a def fill in the gap, and we're gonna provide it a masked sentence, and I'm gonna assume there's just a single mask in a sentence. Otherwise, it becomes a little bit more complicated. We're just gonna do one, and we're gonna say I want to see the top 3, let's say, predictions. Like, what are the top 3 things it could be? And so we have our model. I'm just going to throw it into evaluation mode because there's no other reason to have that. And so first, let's create an example. Let's say our sentence is hello mask. Right, that's our special mask token. How are you doing? Right, that's our sentence. And so we're going to provide to this sentence this fill in the gap function. So let's do that. Fill in the gap, and we're going to provide it our sentence, just like that. And so on this model, we're going to do encoded text, right? We're going to encode our text. This is going to be tokenizer.encode our masked sentence. And because there's already a mask token in there, so encoded text, we will see our mask token appear. So it's for this token. We're curious about what the prediction will be, right? What will it be? What I'm going to do is, first of all, we're going to do input tokens is going to be torch.tensor encoded text, right? We're going to go ahead and encode our text and just make sure it's on the same device where our GPU is currently sitting. So we're going to convert to a tensor, no problem there. And all I need to know is which index. So I know the index here is 2, right? I can see that the index is 2. But I just want to know what's the index of my mask token, and we can quickly find that, right? We can do mask token index is going to be wherever our input tokens is equal to our special tokens index. What did I call it? I always keep forgetting this. I called it the special tokens dict, right? So there we go. That's what I want. And so I want for my special tokens dict, and wherever we have the mask token, right? Just like that. And so we can print out mask token index. It'll just tell me it's true on the, we knew it was on this token, and then everything else is false. And this is just assuming that we have a single mask token. If we had multiple, we'd have to do a little bit more work. I'm just assuming one for now. So fill in the gap. This is just for filling in one thing in the gap. Our data currently, the input tokens, is just a vector. We need to add the batch dimension to it, so we can do that now. We're going to do with torch.noGrad, right? We're going to pass into our model without computing any gradients. Our output is going to be our model, and we're going to pass in our input tokens, and we're going to add a dot unsqueeze 0, right? We're going to add that extra batch dimension in. And now that we've added the batch dimension, and there's no attention mask, right? Attention mask is none, right? We're only passing in a single sample. There wouldn't be any padding masks or anything like that in here. Now that we have everything, we can do predicted output. It's going to be output, and we just want to grab for the first, so 0, right? We're indexing for the first batch. We just want the masked token index, right? We just want the corresponding predictions that go with this specific index. And so this can be print predicted output. These are my logits, right? My raw outputs of what the predictions could be, like what these tokens could be. And so all I want is the top 3 things in this list. So we can do top k predicted is going to be torch.topk, right? I want the top k predicted output. So I want the top 3 most likely outputs. K equals k. So in this case, 3, what we passed in. And we can do dot indices, right? We want the index of them. So we can do print top k predicted. Did I spell something wrong? Predicted outputs. There we go. So these are my predictions. If we don't do the indices, by the way, it gives you something like this. It gives you the values and the, we don't really care about the values. We just care about the index, right, of them, because this is saying the 93rd token in our vocabulary is one of the predictions, and the 6th token is another prediction, and 216 is another prediction. So this is giving me the index in our matrix, right? So again, let's just quickly, we can take a look here. If we see our, I guess this is fine. So basically we're saying that we have this specific prediction for our tokens. These are the 3 most likely things, and these are the indexes in our tokenizer that, what they could be. So whatever, that's fine. And so now that we have that, what we're going to do is predicted words is going to be our tokenizer dot decode, right? We're going to decode, and we're going to decode our top k predicted and just convert it to a list, right? No problem there. And we can then, let's see, dot to list is not a thing that it has because we need dot indices, right? We just want the indexes. Okay, what's the next bug? Bytes, not list. Int argument must be a string, not a list. Okay. So let's just check here real quick. We want to do, let's see, this will convert it, print. So that converts it to this. We have a lists of lists here, but that should be fine. So what could be the problem? So we have tokenizer.decode, int argument must be a string, a byte-sized object, or a real number, not a list. Okay. What could be incorrect here? Let me just try my code real quick. Maybe I'm missing something. Nope. Okay, I'm obviously missing something small. So we have our mask token index. We grab it for our top k predicted outputs, k equals k, and that gives us our top k predicted. What happens if I index this for 0? Oh, there we go. Okay. I guess because it was a list of lists, I guess I should have squeezed somewhere. I'm just missing it. That's fine. Okay, no problem. And what we want to do now is our print predicted words. Right, so these are the predicted things here, which doesn't seem like much, but let's go ahead and try a better sentence. The wizarding mask. Right, let's try to make it relevant to Harry Potter because that's what it's trained for. The wizarding mask is a wonderful place to visit. And we can see the wizarding community, the wizarding world, the wizarding willow. So community and world seems like a reasonable fit for here, right? Or we could try Lord Voldemort. Voldemort is a mask wizard. Is a great wizard, a terrible wizard, a powerful wizard. These are all reasonable fills for what this mask could be. And you can try more. But this basically says that this model understands Harry Potter, at the very least, right? Not English, right? If I put anything in here, it may not necessarily work. Like, for example, we can say, make sure to buy blank, so mask, and eggs. Right? I wonder what it'll say. So up other stones. These are not reasonable fills for this. Right? So it's only trained on Harry Potter, so it only understands Harry Potter. And that's kind of the main idea behind this, right? If we actually wanted to leverage a pre-trained model like this, we kind of need to train it on a boatload of diverse data. And that's why in the next video, we'll be preparing our larger data sets. I can't remember off the top of my head right now which ones they were. I could check. So we will be preparing the Wikipedia and the book corpus dataset. So this will be quite a bit of data, but it will be basically a start to this. So our game plan, prepare the data as the next video. Then we're going to write a full reproduction pre-training script of RoBERTa. So it's going to be basically leverage, accelerate, train on lots of GPUs, that sort of stuff. And the results are already in my Git repo. So this is already done. You can just go look if you want to get ahead. After that, we're going to look at extractive Q&A, which will be a lot of fun. So we haven't really seen any of that yet. Either way, this is all I have for today. I hope this is helpful. Again, if you have any questions, comments, concerns, drop it in the comment section below, and I will see you in the next one.